Good day, everyone, and welcome. We're excited to present our research titled Goal Conditioned Reinforcement Learning for Ultrasound Navigation Guidance. This work by Abdul Aziz Amadou, Vivek Singh, Florin Gesu, Young Ho Kim, Laura Stanciolescu, Harshitha P. Sai, Puneet Sharma, Alistair Young, Ronak Rajani, and Kawal Rode introduces a novel approach to improve ultrasound navigation. Our goal is to enhance training for sonographers and improve acquisition quality. Stay tuned to learn about our versatile model that navigates robustly to both standard and arbitrary views. Thank you. In this slide, we delve into the key highlights of our research. Our primary motivation is to enhance ultrasound navigation using a novel approach, goal-conditioned reinforcement learning. We believe this method can be instrumental in training sonographers, improving the quality of image acquisition, and reducing variability among experienced users. We've addressed significant challenges in this field. Our model is capable of navigating ultrasound images to both standard and arbitrary views, a task that has been a hurdle in the past. Moreover, our goal-conditioned reinforcement learning model stands out due to its versatility and robustness. It's not just about reaching the goal, but how effectively and efficiently we can get there. In the next slides, we will delve deeper into the specifics of our model and how we've managed to overcome these challenges. Stay tuned. Moving on to the key highlights of our research. Our main method utilizes goal-conditioned reinforcement learning. This innovative approach allows our model to navigate robustly to both standard and arbitrary ultrasound views, given a goal image. The model was trained using the LIDC IDRI database, a valuable resource provided by the National Cancer Institute and the Foundation for the National Institutes of Health. This extensive database has been instrumental in the development and testing of our model. Lastly, it's important to note that the performance of our model is highly dependent on the agent's exploration of the environment during training. This means that the more diverse and comprehensive the training data, the better the model performs in navigating to the desired ultrasound views. In essence, our research presents a promising step towards improving ultrasound navigation, with potential applications in training sonographers and enhancing the quality of image acquisition. Begin frame title key highlights. Begin itemize. Item Our key contribution is a novel approach of using goal-conditioned reinforcement learning for ultrasound navigation. This is a significant step forward in the field, as it allows for a more versatile and robust navigation system. Item Our model is not limited to standard views. It can navigate to both standard and arbitrary views, showing specific structures. This versatility opens up new possibilities for ultrasound imaging and could potentially improve the quality of the scans. Item This approach could also be used as a training tool for sonographers, helping them to improve their skills and reduce variability in their work. End frame. Moving on to our key highlights. Our model achieves competitive performance when compared to specialist models. This is a significant achievement as it demonstrates the versatility of our approach. Furthermore, our model can robustly navigate to arbitrary views without the need for explicit sampling during training. This is a testament to its adaptability and robustness. However, it's important to note that our model does require a longer training time. This is due to the contrastive critic needing a large number of samples to converge. But don't worry, we've found a solution to this. By using an efficient asynchronous implementation with RLlib, we've managed to reduce the training time to just 2 days for 200 million steps. This is a major step forward in making our model more efficient and practical for real-world applications. In summary, our model is versatile, robust, and efficient, making it a promising tool for ultrasound navigation. Begin frame title Goal-conditioned reinforcement learning. Begin figure. Centering. Include graphics. Width equals 0.8 text width. Height equals 0.45 text height. A SRC task _ execution extracted _ paper _ data. 2405.01409 v1. Figures. 2405.01409 v1 figure 2:1.png. Captiona Tinea, the actor-critic architecture of our goal-conditioned framework. The critic predicts the probability of reaching a goal given an observation and action, while the actor outputs the action to take to reach the goal. Contrastive learning is used to train the critic function. End figure. Begin itemize. Item unveiling our goal-conditioned framework. Begin itemize. Item actor-critic architecture. The critic predicts, the actor performs, item contrastive learning. Enhancing the critic's training, item addressing the reality gap. Potential fine-tuning for real-world deployment, end itemize, end frame. Moving on, let's delve into the heart of our study, the goal-conditioned RL for ultrasound navigation system. As you can see in the figure, our system takes CT scans, segments them, and generates ultrasound volume reconstructions. This allows for rapid sampling during the training phase. The model is trained to reach randomly selected goal views using a mechanism we call contrastive patient batching. Now, why is this important? The quality of ultrasound imaging is directly impacted by the ability to navigate to the correct views. Furthermore, this system can be a valuable tool in training sonographers, providing them with a robust and versatile model that can navigate to both standard and unique views. In essence, our system is designed to improve the quality of ultrasound imaging and enhance the training of sonographers, making it a significant contribution to the field. Moving on, let's delve into our proposed solution. Goal, conditioned reinforcement learning. As you can see in the figure, our system segments CTs and generates ultrasound volume reconstructions for rapid sampling during training. This novel approach for ultrasound navigation is what sets our work apart. Our model is not just versatile, but it also navigates robustly to both standard and arbitrary views. This means it can adapt to a wide range of scenarios, making it a powerful tool in the field of ultrasound navigation. The contrastive patient batching, or CPB mechanism, allows the model to reach randomly selected goal views during training. When deployed, the model can navigate to any view, including standard and interventional views. This flexibility and adaptability are key features of our approach. Begin a frame. Frame title: a model performance and versatility. Begin a figure. Centering. Include graphics. Width equals 0.8 text width. Height equals 0.45 text height. At SRC task _ execution extracted _ paper _ data 2405.01409 v1. Figures. 2405.01409 v1 figure 2:2.png. Caption: a tiny comparison of our model with existing methods in reaching standard views. Our model demonstrates robust navigation to both standard and arbitrary views. End a figure. Begin itemize. Item model comparison. Begin itemize. Item: our model outperforms existing methods in standard view navigation. Item demonstrates robust navigation to arbitrary views. End itemize. Item versatility. Begin itemize. Item can navigate to views not explicitly sampled during training. Item shows potential for real-world deployment with further fine-tuning. End itemize. End frame. Let's delve into the challenges and solutions we encountered during the training of our model. One of the main challenges was the longer training time. This was due to the need for many samples to converge. However, we found a solution to this issue by implementing an efficient asynchronous method using RL-lib. This significantly alleviated the training time, making the process more efficient. The figure you see here provides an overview of our goal conditioned RL for ultrasound navigation system. It illustrates how the system segments CTs and generates ultrasound volume reconstructions for rapid sampling during training. The model is trained to reach randomly selected goal views using the contrastive patient batching mechanism. When deployed, the model can navigate to arbitrary views, including standard and interventional views. This demonstrates the versatility and potential of our model in real-world applications. Let's delve into the practical application of our system. As you can see in the figure, our goal conditioned RL for ultrasound navigation system segments CTs and generates ultrasound volume reconstructions for rapid sampling during training. The model is trained to reach randomly selected goal views using the contrastive patient batching mechanism. When deployed, the model can navigate to arbitrary views, including standard and interventional views. However, deploying this system in real-world settings presents its own set of challenges. There may be a need for fine-tuning using real data or improved simulations to ensure the model's performance. This is crucial to address what we call the reality gap, the difference between our training environment and the actual practical application of the system. This step is vital to ensure the system's robustness and reliability in a real-world setting. Moving on to related works, let's first take a broad look at the field of ultrasound navigation. This area is rapidly evolving, with reinforcement learning playing a pivotal role in its advancement. It's fascinating to see how these techniques are being applied to navigate ultrasound images, enhancing both precision and efficiency. Now, let's delve into the specifics of goal condition reinforcement learning, a key concept in our study. This approach defines a navigation task with several components, including the environment state, the set of possible movements, and the goal condition reward function. It's a complex system, but at its core, it's about determining the best action to reach a specific goal. The framework we use is based on the actor-critic architecture. Here, the actor decides the best action to take to reach the goal, while the critic evaluates the probability of reaching the goal with that action. It's a dynamic interplay that allows for robust navigation. In the next slide, we'll delve deeper into the specifics of our model and how we've implemented these concepts. Stay tuned. In this slide, we delve into the related works. First, we discuss contrastive learning. This technique is used to train the critic function in our model. It involves two models, phi and psi, which play a crucial role in encoding state, action pairs, and goals. This approach allows our model to learn effectively and navigate to the desired views. Next, we compare our approach with existing ones, such as RLT, SAC, and CRLD. While these methods have their merits, they also have limitations. For instance, they are not goal conditioned, meaning they can't adjust their behavior based on a specified goal. Moreover, they require separate models for each view, which can be inefficient. Our model, on the other hand, is versatile and can navigate to both standard and arbitrary views, demonstrating its robustness and adaptability. This makes it a promising tool for ultrasound navigation, potentially improving acquisition quality and reducing variability among users. In this slide, we delve into the training process of our model. We initialize the transducer at a given pose and apply random perturbations to obtain the starting pose. This ensures our model is always trained with random goals, enhancing its versatility. We also use landmarks extracted from automatic segmentations and follow clinical guidelines to find probe poses, which helps in obtaining standard views. Next, we discuss the role of data-augmented contrastive loss in our training process. We use a randomly shifted version of the observation and goal images, which we refer to as data augmentation. This technique helps the critic function to generalize better by learning from a variety of data. The random shifts in the observations and goal images play a crucial role in this process, ensuring a diverse range of data for the model to learn from. In essence, our training process is designed to maximize the model's ability to navigate to both standard and arbitrary views, making it a robust and versatile tool for ultrasound navigation. Moving on to related works, we have the contrastive patient batching, or CPB. This strategy is crucial for the convergence of the critic in our model. The issue with a randomly sampled batch is that it contains samples from different patients, each with unique intermediate states. This diversity can lead the critic to learn features associated with the anatomical differences between patients, rather than the general anatomical features necessary for the control task. To address this, we tag the trajectories by the corresponding patient identifier during training. In creating a batch, we sample triplets from two patients, ensuring a significant number of samples come from the same patient. This creates harder negatives for the critic, improving its effectiveness in discriminating trajectories. This strategy has proven to be a significant step forward in our research. On this slide, we delve into the technical details of our proposed research. The figure you see here provides a system overview of our novel approach, which uses goal condition reinforcement learning for ultrasound navigation. This method is not only versatile but also robust, capable of navigating to both standard and arbitrary views that display specific structures. This versatility is a key strength of our model, allowing it to adapt to a wide range of scenarios and tasks. In the following slides, we'll explore how this approach works in more detail and discuss the results of our experiments. In this slide, we delve into the technical details of our research. The figure you see here provides an overview of our system for goal condition reinforcement learning in ultrasound navigation. We start by formulating our problem. We define the goal condition navigation task using several elements. These include the environment state, the set of transducer movements, transition probabilities, the goal condition reward function, and the set of observations. Our framework employs an actor-critic architecture. The actor and critic work in tandem, with the actor deciding the best action to reach the goal, and the critic evaluating the probability of reaching the goal with the chosen action. This approach allows us to create a robust and versatile model for ultrasound navigation. Stay tuned as we delve deeper into the specifics of our model in the upcoming slides. In this slide, we delve deeper into our approach to the problem. We utilize contrastive learning to train a critic function. This function is key to our model as it measures the similarity of latent representations through an inner product. This means that when an action is likely to lead to a goal from a given pose, the inner product will have a high value, indicating a high probability of reaching the goal. Now, let's talk about the actor in our model. The actor learns to output the correct actions by maximizing the output of the critic. In simpler terms, the actor's role is to take the best possible action to reach the goal based on the critic's feedback. The figure here provides a system overview of our goal. Conditioned reinforcement learning for ultrasound navigation. It's a visual representation of how our model works, from the input of the observation and goal to the output of the action. In essence, our approach combines the strengths of contrastive learning and reinforcement learning to navigate ultrasound images effectively and efficiently. In this slide, we delve into the technical details of our research. The figure you see here provides an overview of our goal: conditioned reinforcement learning system for ultrasound navigation. Our experiment design begins with the initialization of the transducer at a specific pose, and a goal observation is provided. The training process involves the computation of critic and actor loss. The critic loss helps train the critic to predict which actions lead to a goal, while the actor loss guides the actor to output correct actions. We also employ a data-augmented contrastive loss and a technique we call contrastive patient batching, or CPB. This involves tagging trajectories with patient identifiers during training, which helps the critic learn general anatomical features necessary for the control task, rather than focusing on differences between patients. These techniques together form the backbone of our innovative approach to ultrasound navigation. In this slide, we delve into the technical details of our research. The figure you see here provides a system overview of our goal: conditioned reinforcement learning approach for ultrasound navigation. Now, let's talk about the key improvements and innovations we've made. Firstly, our model's performance is intricately tied to the agent's exploration of the environment during training. This means the more the agent explores, the better the model performs. Secondly, our model has the unique ability to robustly navigate to arbitrary views. This is achieved without explicit sampling during training, showcasing the versatility of our approach. Lastly, we've managed to alleviate the typically long training time associated with contrastive reinforcement learning. We achieve this through an efficient asynchronous implementation, significantly speeding up the process. These advancements collectively contribute to a more robust and efficient ultrasound navigation system. On this slide, we delve into the key results of our research. Our proposed model shows competitive performance when compared to specialist models, even though it's trained to navigate to multiple views. It's capable of robustly navigating to any given view without needing explicit sampling during training. We tested the model in two scenarios: one where the goal is a synthetic US view from the same patient, and another where the goal is a US view from a different patient. The model's performance was measured in terms of position and angle error at the end of each episode, relative to the ground truth pose. Lastly, we evaluated the model's ability to navigate to a non-standard view used in law closure procedures. This demonstrated the versatility and practicality of goal conditioning in ultrasound navigation. The figure you see here provides a system overview of our goal conditioned RL for ultrasound navigation. It's a visual representation of the process and components involved in our novel approach. Moving on to our conclusions and remarks. We've developed a novel approach for ultrasound navigation using goal-conditioned reinforcement learning. This versatile model can navigate to both standard and arbitrary views, showing specific structures. It's important to note that the performance of this model is highly dependent on the agent's exploration during training. Our model achieves competitive performance when compared to specialist models. However, it does require a longer training time due to the contrastive critic needing many samples to converge. But don't worry, we've managed to alleviate this with an efficient asynchronous implementation using RLlib. In essence, we've created a robust and versatile tool that, despite its longer training time, shows promising results in the field of ultrasound navigation. Thank you.